This is the Python tutorial for the 2021 Boulder Statistical Genetics Workshop. I'm Cotton. On the 18th, my colleagues Tim Paturba and Kumar Virapin will cover DNA sequencing technologies and introduce HALE, a Python library that we've developed for analyzing large-scale genomic data. The purpose of this tutorial is to cover the basics of Python to make it easier to understand and follow the HALE tutorial for someone who's never used Python before. If you've programmed in Python, you probably don't need to watch these lectures. We also think that Python is an excellent tool for bioinformatics, and I've tried to cover other basic useful material beyond just what's needed for the introduction to HALE, in case you start using Python in your work. I've also written this lecture up as a Jupyter notebook that you should have a copy of for reference. However, in this lecture, I'm going to start from scratch in an empty Jupyter notebook. This is the Jupyter dashboard, which is how Jupyter opens when you start it. It opens to a file browser where you can see files on your computer, including other Jupyter notebooks that you might use, like the ones we'll use for the HALE practical. Although for this tutorial, I'm going to start in a new, fresh Jupyter notebook. My advice for getting the most out of this lecture is to follow along in your own Jupyter notebook, typing in the examples along with the video. This will help you engage actively and start developing muscle memory for typing Python syntax. You should have instructions on how to install and get access to Python in Jupyter. You may want to pause now and get that set up before you continue. So this is a Jupyter notebook. Jupyter notebook is made of cells. Cells are blocks of code or text that are independently editable and executable. So, not a very interesting notebook yet, so let's put some code in there. So the first program you write in any programming language is the Hello World program. To execute the code in a cell, you press Shift-Enter, and the result of executing the shell, the result of executing the cell is placed after the cell. So you can see we get Hello World on output. Let me go over a few features of Jupyter. You can see that the current cell that's selected is in green. That means we're in edit mode, which allows you to edit the contents of a cell. If you hit escape, the highlight turns to blue, and that puts you in navigation mode, where you can move between cells and manipulate cells. So we can use the up and down arrows to move up and down. To go back to edit mode, you just hit enter, or you can click on a cell. Maybe we didn't want the comma, and then Shift-Enter reruns the cell. So just a reminder, it's escape to go to navigation mode, it's enter or click to go to edit mode, and Shift-Enter to evaluate a cell. I'll say briefly that there are two cell types, code and text. Jupyter notebooks are used both for developing data science analyses as well as presenting them, so it allows you to intersperse documentation and other figures and other information with the code of your analysis. So let's convert this cell to a markdown cell. So text is written in markdown in Jupyter. So if you're in navigation mode and you hit M, that converts the current cell into markdown mode, and you can see that the little cell type drop-down in the toolbar changed to markdown. And here we can say a Jupyter cell. There are two types of cells, code, text. And you can also include math in Jupyter Markdown. Let's say this is LaTeX for, let's say mu equals one n sum of x. Right, so this is embedded LaTeX mathematics inside of a markdown cell in Jupyter. So this is great for doing math and statistics and other documentation. Okay, back to Python. So Python has numbers, integers and floating point numbers, like most languages, and it works pretty much like you'd expect. Plus, minus, and times and parentheses do the normal thing. So if we make a simple arithmetic expression like 5 times 3 minus 1, we're going to get 10. There are both integers and floating point numbers, so we can have something like 3.14, and if you add 5 to that, you get 8.14, so all of the arithmetic operators convert integers to floats if there's a mixture of integers and floats. We've now seen a couple of different types of values, strings, like in the Hello World program, as well as numbers. Every value in Python has a type, and often when you're getting started, it's useful to be able to inspect values and see kind of what they are and how you might work with them. So one of the ways to do that is this type function. And type function takes a value, and then it prints out the type of that value. And if we do 3.14, we see that's a floating point number. So that can be useful when you're starting to get oriented and you have a value that's not behaving like you expect. You can print out its type and understand what it is. The one thing that's unusual about Python is that there are actually 2 division operators. The single slash division is floating point division. So even if both of the inputs are integers, you get a floating point on the output. There's another version of division, which for integer division, which does integer division and rounds down. That's actually a bad example. So let's do something more like 8 divided by 5, and we're getting a 1. So that's just a thing to remember: single slash, floating point division, double slash, integer division, rounding down. Rounding down might seem like a slightly strange choice. Whoops, sorry, I meant double slash there. So if you do minus 2 divided by 5, that's going to be minus 0.4, but when you round down, you get minus 1. Integers in Python are arbitrary precision, so you can do very large mathematics and things will just work out of the box. So for example, let's do 2 to the double star operator is the exponentiation operator. So 2 to the 1,000, very big number, but Python has no problem representing it. And of course you can do things like comparisons. 5 is less than 7, that's true. 5 does equal 7, but 5 does equal 5, but 5 does not equal 7. So there are 2 new values, true and false. Those are Boolean values. Whoops, typo there. True is true. There are 3 logical connectives, and, or, and not. They're spelled out with words, so true and false is going to be false, and true or false is going to be true, and not true is going to be false. You assign variables using the equal sign. So my variable equals 5. Assignment doesn't print anything out, so you'll need a separate statement to see the value of your variable. And one of the ways I like to do that is actually do the assignment and then put the variable right afterwards. So then we get the value of the assigned variable as well as assigning the variable. Great. The next primitive type is strings. So as we saw above, strings can be written with single quotes. Strings can also be written with double quotes. And there's no difference between the underlying strings. You see that Python has a preference for printing strings with single quotes when you evaluate them. So it doesn't matter if you use single or double quotes, you get the same string. So for example, ABC with single quotes is equal to ABC with double quotes. And one of the reasons why this is useful is sometimes, especially if you're generating error messages for a user, you might want to use quotation marks or single quotes inside of your text. And if you use the other kind of string, that will make the formatting a little easier. So for example, if I want the string that has the word can't and won't, if I use double quotes, then I can just write the single quote. But if I use single quotes, I have to escape the single quote. I think that gets me the right thing, right? And here, Python prefers to print it with double quotes because it contains single quotes. There's one more type of string, which is called an F string or an interpolated string, when you're generating messages for the user, you often want to mix text that you write with values that are computed as part of the program, say if you're trying to report the result of an analysis. And so f-strings make it really easy to construct strings in that case. So let's do an example where suppose I'm analyzing some genetic data and I have a trait, which is going to be blood glucose. And I do some statistical test on my blood glucose trait, and I'm going to get a p-value of 0.002. And then I want to report this to the user. So I'm going to write an f-string, which is just like a normal string, except it starts with the letter f. And then you have text. The p-value for the trait is p-value. Right? And so what f-strings do is whenever there is a pair of curly braces, the f-string interprets the contents of the curly brace as a Python expression. It evaluates that Python expression, and then it puts the result of that into the string. So what we're going to get is the p-value for the trait, for the blood glucose trait, is 0.002. And we'll make extensive use of this. This is really useful. Okay, so in a lot of ways, Python is a pretty straightforward language, but there's a couple of things that are a little unusual. And this is the first one. This is the way that Python handles blocks. So in most programming languages, or a lot of other programming languages, code blocks are often indicated inside of curly braces. But Python does something else, and it defines blocks by sequences of statements with the same indentation level. So let me show an example to hopefully make sense of this. So I'm going to have a conditional that's false, so this is not going to run the contents of the if. And let's say print first, and then I'm going to print really first. Okay, so I'm going to insert another cell. So here's a Jupyter Notebook trick. If you're in navigation mode and you hit B, it inserts a cell below your current cell. And if you hit A in navigation mode, it inserts a cell above the current cell. This can be useful for inserting things and manipulating. If you inserted some cells that you don't need anymore, you can press double D inside of navigation mode, and it will delete the cell that's currently selected. Okay, so there's our first example. The first piece of code is this false with two pieces of indentation, and I want to compare this to false print first, print really first. Right, so when we run the first example, what's going to happen is the conditional will be false, so first will not be printed, but then we'll go to after the conditional, and then we'll print really first. But in the second example, both statements are inside of the if because they're at the same indentation level. And therefore, neither statement will run, and there will be no output for the second program. So let's verify that by evaluating these. We just get really first, and then we get no output. So this shows a surprising fact, which is that the white space in the program actually can affect the result of the program. And this is known as being white space sensitive, or indentation sensitive. Which is kind of a unique feature of Python. Most programming languages, when you create blocks using, say, curly braces, like a C program. Here's a little mini C program that uses statements inside of curly braces. Usually you use curly braces and you indent. Right? But the indentation is not significant, it's just convention. And so what Python said is we can get rid of the extra symbols related to curly braces and defining blocks by relying on the indentation to tell us where the blocks begin and end, which I think leads to a quite elegant syntax. You'll notice that anytime we had a line that ended with a colon, we increased the indent for the following line, and that is always true in Python syntax. So if you indent without a preceding line with a colon, or you don't indent when there's a colon, you'll get an error in Python. So let's see two examples of that. So say we're going to assign x equal to 1, then I'm going to indent and assign x equal to 2, y equal to 2. But the x equals 1 line didn't end with a colon, so this indentation is incorrect, and we will get an error, unexpected indent. Similarly, say we have a conditional that we're going to say is true, so we're always going to execute this. And then if we say, this is a mistake, and we evaluate this, well, Python said, well, there was a line that ended with a colon, so I expected indentation in the next line, and it wasn't there, so that was an error. Great, and we've been talking about conditionals, so I'll just give a few more details with conditionals. You saw that there's an if that can have a then arm. You can actually have slightly more complicated conditionals. So let's say we have some number that we're interested in, in branching on I equals 1. And then we're going to say if I equals 0, print, well, we're in the first slot. If you want to chain multiple ifs together, you can use the else if clause in Python. And that looks just like an if, but it follows another one. So then if I equals 1, second. And then finally, you can have an else clause. And an else clause runs if none of the preceding ifs match. And here we can print, say, the nth. We're just like something bigger than 1. Right, and we evaluate this, and we get second because I equaled 1. Now let's talk about lists. Lists are one of Python's main data structures, and they're a compound data structure because they contain other values inside of them. Lists in Python are similar to arrays in other languages. They're linear sequences of indexable values, but in Python, lists can grow and shrink. Let's look at an example. Lists are written in square brackets with the elements listed between with commas in between the elements. So let's say we've got some DNA sequences, most of which have a single base, but then we'll add one with a double base. Then we'll print it out. You can see we have a list. The list has 4 elements. You can use bracket index notation to get the list. Lists are indexed starting at 0. So the first element, which is A, you can get by doing A of 0. That would make the last element A of 3. You can get there's a function to get the length of a list, len A. And Python is a safe language, so it's going to check for errors in the program as it runs. So for example, if you try to index past the end of a list, you're going to get an exception, index error, list index out of range, and Python shows the offending line so you can go back to your code and see what happened and where it happened. Maybe one surprising feature of lists that you want to be aware of, it would look like A of -1 would be another index error because you're going off to the left side of the list. But in fact, array indexes interpret negative values as starting from the end of the list and moving towards the beginning of the list. So A of -1 is actually the last element of the list, AA, and A of -2 is the second to the last element of the list. Lists are mutable data structures, so you can modify them. So for example, if we can just use an assignment statement with a list index on the left-hand side to change a list element. So let's change this to TTT. And let's print out the list. And we see that the second element is now TTT. You can also add elements to the end of the list with the append operation. This modifies the list, so when we print it out now, we see there's a G element in the back. You can also remove an element from the end of the list with the pop function, and now you see that that element is gone. Okay, one of the things you might want to do with a list is iterate through its elements. And I'm going to show 2 ways to do that. The first, which is maybe the most complicated, but also the most straightforward, is to use a loop using an index variable that iterates through the elements of the list. So we're going to do something like, we're going to start at the first position of the list, so we set our index variable I to 0. And then, while I is less than the length of the list, we're going to say, in this case, let's print out the elements of the list. And so we'll get the ith element of the list and print it out, and then we'll move on to the next element. This kind of programming won't be necessary for the Hail tutorial, so if you haven't seen this before or it doesn't totally make sense, that's okay. We'll look at some other ways that might be more straightforward to do iteration through lists. So we run that and we see we get the 4 elements of the list printed out one at a time. This is such a common idiom in Python that there's a special syntax for it, iterating through the elements of the list, and that's a for loop. So the for loop looks like this for x and a. So for x and a says, iterate through the elements of the list, each time binding an element of the list to the variable x, and then execute the body of the for loop. And here, we just want to print the elements out, so we're going to just say print x. And we evaluate that, we get, again, the 4 elements of the list. So Python is a very popular programming language, and this has a lot of benefits. And one of the benefits is that there are an incredible number of Python packages that you can use when you're programming with Python to do kind of all sorts of things. You want to analyze large-scale genomic data? Check out the Hail package, which we'll be talking about later in the workshop. If you want to control your home smart thermostat, there's a package for that. The packages are published on something called the Python Package Index. So that's pypy.org. And you can see there are 300,000 Python projects with 2.5 million releases that you can sort of take advantage of. I don't find the Python Package Index website search super great. There's the sale library. So often I search on Google for packages that are relevant, and many packages have their own home pages, and that actually has more information about what the package is and whether you might want to use it. So, but checking PyPy can also be useful. Okay, there's a tool, which we won't go over here, called pip for downloading and installing Python packages. Once you have a package installed, you can use an import statement to get access to the package in your program. And so let's look at a little example where we're going to sample from a uniform distribution on 0, 1. So it turns out Python has a built-in package that comes with Python for sampling random numbers. That's called the random package. So we're going to say import random. So this adds a new symbol in our environment, which is the random package. We can actually just say random. You can see this is a module that came from the Python installation. The random module, you can access elements of modules with dot syntax. So inside of random, there is a function called random. It's a little random. And that function samples from a uniform distribution on 0, 1. So let's call that function random, and we get a number, 0.85. If we evaluate the cell again, we did get a different number, 0.65, right? Because this is generating randomness. So the next thing I wanted to do is create a list of random samples from the uniform distribution on 0, 1. Let's create 1,000 of them. Okay, so the syntax for creating arrays, lists that we saw before, concretely needed to know how many elements they had. So if we look back up here, right? We're listing the elements explicitly in square brackets, but we don't know what the elements are beforehand here. We're going to have to construct them programmatically. So what we're going to do is we're going to start with an empty list of samples. And then while the list has fewer samples than we're trying to get, we're going to keep sampling and adding them to the list using the append method that we saw earlier on lists. So we'll say, while the length of samples is less than 1,000, well, we want to sample by calling random and adding it to the list using append. So samples.append, random.random. Right, and then let's print out samples just to see what we got. Right, and when your output is very big, Jupyter automatically introduces a scroll bar to make things manageable, and we can see we just have a lot of random samples from the uniform distribution. And we can just verify that the length of the samples is 1,000, like we hoped it would be. There's actually another way to write this using a somewhat advanced feature called list comprehensions. So before we come back to this example, let me introduce list comprehensions, and then we'll show how to write this example in a simpler way using list comprehensions. Much in the same way that we could explicitly iterate through a list using an index variable, but the for loop gave us a more concise syntax for iterating over lists. Okay, so let's say we have a list, 1, 3, 2, and that we want to create a new list, which is the square of each element in the first list. So it's called a squared x. And we're going to start empty, and then we're going to iterate through the x list, and then we're going to square each element and then add it to the squared x list. So for the ith element of x in x, we're going to add to squared x, xi squared. And remember, the double star operator is the exponentiation operator. So we get the square, and then let's print out squared x. Right? And we get 194, just like we hoped. Great. This idiom is also incredibly common. So Python has introduced a special syntax for doing exactly this, which is a list comprehension. And that looks like this: xi star 2 or xi in x. And this basically says construct a new list whose length is the same as x, and each element of the new list comes from the old list x by squaring each element. And so if we evaluate this, we see we again get 194. This is super concise. List comprehensions are awesome. Great. So this is a case where you can construct a list from a pre-existing list to get one of the same size. But our previous example, going back to the random sampling, we didn't have a pre-existing list with the right number, with 1,000 elements from which we could use to iterate over using comprehension syntax. So Python has a thing called range. And range gives you effectively a list whose elements are 0, 1, 2, up to n minus 1, n elements. And so if we do range 5, we see we get a range from 0 to 5, where 0 is included and 5 is excluded. So this range object is not actually a list, but it behaves otherwise identically to a list and is otherwise more efficient. So you can iterate through the elements of a range with a for loop, and it will have the elements 0, 1, 2, 3, 4. So now we can use array comprehensions along with range to create a 1,000 element list where each element is a random sample of the uniform distribution on 0, 1. So we're going to call random.random, and then we're going to say for I in range 1,000. Note here that I isn't used. We don't actually care about the index. We just care about the fact that range has 1,000 elements. So when we use a list comprehension to create a new list from range, it will also have 1,000 elements. And we evaluate, and we see that we get, indeed, 1,000 random samples from the uniform normal distribution on 0, 1. Okay, next let's talk a little bit more about functions. We already saw that you can call a function like type by giving the arguments to type in parentheses afterwards. There are lots of functions in Python. Python has a min function you can call when it takes multiple arguments. There's actually two kinds of functions in Python. Normal functions that we've seen already, and something called methods. And methods are part of object-oriented programming. And a method is basically a function which is associated with an object or a value in Python. And methods are called with dot syntax. So let's look at two related functions, one a function, one a method, that do basically the same thing in a slightly different way. So let's go back to our example of a list x 132. And let's say we want to sort this list. Okay, so Python has a function called sorted, which will take a list as input, sort the list, and return a new list that is the sorted version of the first list, right? So we get 1, 2, 3. I need to create a new cell. Great. I'll just note that the list x was unchanged, so we still have the old list that is 132. Okay, there's another function in Python that sorts a list, but it does it by modifying the list in place. And that is a method called sort, which is used using the dot notation to invoke. Right? So you can see when we run sort, we get no output. Sort doesn't return anything because it's modifying the list that it's sorting rather than creating a new list. And so now if we print out x, we'll see that we get 1, 2, 3. So normally when you pass arguments to a function in Python, you pass them by position, like when calling the min function with 5 and 7. However, there are some functions that can take another kind of argument called a keyword argument, where you actually say the name of the parameter that you're passing when you're calling the function. And keyword arguments are often used for optional flags or parameters to functions to control their behavior. So let's look at an example. Let's go back to x, which is 1 through 2. I'm going to sort it again. Now I'm going to look at I'm going to look at two different invocations of sorted. So we already saw, let's evaluate x, and we already saw if we sorted x, then we get 1, 2, 3, and x is unchanged. Now, what if you want to sort in the opposite order? You could use sorted and you could reverse it, but actually sorted has an option for reversing in the opposite order, which is a reverse keyword argument. So I'm going to say, I'm going to call sorted, I'm going to give it x, and then I'm going to give it another parameter by name called reverse, which I'm going to set to true. And so now when we sort, we get 3, 2, 1. And the Python documentation and the Hail documentation will explain what the parameters are and what the keyword parameters, what the parameters are and what the keyword parameters are, so that you can understand how you can use the different functions. Okay, so up to now, we've been calling functions, but we'd also like to be able to define functions. So let's define a little function. And let's have that function take an argument and then limit its value to be in the range of 0, 1. So let's call this function cap. And functions are defined by using the def keyword. Okay, and so we're going to define a function called cap. It's going to take one argument, which is going to be a number, and then we're going to bound it in the range 0, 1. Okay, def statements, lines with a def in it end with a colon. So we need to increase the indent to signify the body of the function that we're defining. Okay, and now we're just going to use if to check the conditions of whether or not it's outside the range of 0, 1 and act appropriately. The last thing I'll say is to return a value from a function, you use the return statement. So let's look at that. So if x is less than 0, then we're outside of the range of 0, 1, and we want to return 0. If x is greater than 0, then we're outside, if x is greater than 1, then we're outside the range 0, 1, above, and we want to turn 1. Otherwise, now we're in the case where x is between 0 and 1, and we can just return x. Right? Okay, so we evaluate that, and it generates no output, and it defines the cap function. We can look at cap, and we can see cap is a function. So let's test it. Let's call it on 3 examples, one with -5. So we expect to get 0, because -5 is below the range 0, 1. Let's look cap of 3, and then let's look at something where it is in the range 0, 1. And indeed, our function works. If it's below 0, we get 0. If it's above 1, we get 1. Otherwise, we get the value itself. Great. Let's define a couple other simple functions just to get some practice. So we generated this list of samples from 0, 1, from the uniform distribution on 0, 1. So let's write a function that will take this list as an argument and compute its mean. Pretty straightforward statistical thing to do. And remember, we had the equation for the mean. It's going to be the sum of the elements divided by the number of elements. We can use the length function to get the number of elements. So we just need to compute the sum. So, right. So what we're going to do is we're going to iterate through the elements of x, adding them to an accumulator variable that is keeping the running sum of the elements that we've seen so far. So I'm going to call that variable 0. Call that variable s, and then to start, set it to 0. And then for each element in x, I'm going to assign it, I'm going to add it to s. There's actually a shortcut for that syntax, which is the plus equal operator. And this says add x into s, setting it as the new value to s of s. Okay? So then after we're done with the loop, we just need to divide that by the number of elements. So we're going to return s divided by length of x. Here we want a floating point division, so we use a single slash. Okay, and then let's test it on an example. And let's just cook up some random numbers. All right, that's going to be, sum is going to be 1.8 divided by 3. We should get 0.6. And I had an error. Great, my error was that I wrote x here, which is a list, x here, which is a list, rather than xi, which is an element of a list, which should be a number. And then I get an error saying that I can't use an int in a list in a plus equal statement. Great, we change that to xi and we try again, and lo and behold, we get 0.6 as we expected. There's actually an easier way to do this in Python. Turns out there's a function that takes a list of numbers and gives you the sum. So we could actually have written this. Sum of x divided by length of x. Right, and then let's do the same test. Copy that, paste it down here. And indeed, we get a new mean function, which is a little simpler. That also works. So I mentioned there's lots of packages. One package, if you start using Python, that you'll certainly run into is NumPy. It's a scientific numerical computing library. It's ubiquitous in its use. NumPy is normally imported using this as statement, which renames it to NP. It's kind of a common thing to import major packages with a two-letter nickname. And of course, NumPy has a mean method, which we could have just called directly instead of writing our own. Great. So next, I would like to talk about the next compound data structure that we're going to encounter, which are tuples. And tuples are very similar to lists. You might even wonder why I have both tuples and lists. There are basically two main differences between tuples and lists. One is that tuples are written with round parentheses instead of square brackets. And the second difference is that tuples cannot be modified. So let's actually give this tuple a name. T for tuple, or not T. Right, so you can index the elements of a tuple with the square bracket index notation, just like you can with lists, but you cannot assign tuples. They are immutable. Right, tuple object does not support item assignment. Tuples are not modifiable. Tuples don't have an append element. Right, no append attribute because you can't modify a tuple. Why are tuples used? And so this is I would say is mostly a matter of convention. In many cases, you can use tuples or lists. There's the convention that often you use lists for data structures where each element of the list has the same type, like we saw above, where we had an array of a list of numbers. Whereas tuples are more often used when the elements of the tuple have different types, like the example that I used that has the number 0.5 and the label midpoint. There's another place where tuples are often used, which you'll actually see in the Hail interface during the Hail tutorial. Tuples are used to return multiple values from a function. So normally you'd have a single return value, but if you have multiple parts that you want to return, you can package them up in a tuple and return that. So let's look at a little example where, okay, we have a function for computing the mean. Let's write a function for computing the variance, and then write a function that takes a list of numbers and returns a tuple which has its mean and its variance. Great. So let's start by recalling the definition of variance. So I'm going to make a markdown. Cell so I can write some text to describe the equation of the variance. And so to switch between code and markdown, we're going to go into navigation mode. And if we hit Y, that will put the cell into code mode where we can write Python. And if I hit M, that will put the cell into markdown mode so I can write text with markdown. And so here we're going to say the definition of variance is, so I'm going to write a little latex. Don't worry if you don't understand this. So we're going to use the definition of the variance as the difference between the expectation of the squares and the square of the expectation of your list of numbers. Great. So the expectation is just the mean, and we already have a function to compute the mean, so we're going to use that to compute the first term and the second term. So let's define a function. We're going to call it variance. It's going to take a list of numbers as an input. We're going to use a colon, start indentation to mark the body of the function. And then we're going to take the mean, and then using a list comprehension, we're going to take the list that we already have, x, and then we're going to construct a new list, which is the list of squares of the elements of x. And we already saw basically how to do that. xi for xi and x using a list comprehension. And then we're going to subtract the mean of x squared. Very concise. Between for loops and list comprehensions, you can write a lot of stuff very concisely. So let's test that on our list of samples from the uniform distribution on 0, 1. And we get 0.081. So is that a good answer? So it turns out if you analyze it analytically, the variance of the uniform distribution on 0, 1 is 1 divided by 12. So with 100 samples, we got pretty close. Great. So now we want to build a function that, given a list of numbers, returns both its mean and its variance as a tuple. The mean and the variance are the parameters of a normal distribution. So effectively, we're finding the best fit normal distribution to the set of samples that we're given. So let's call this fit normal. And it's going to take a list of numbers, and it's going to return a tuple that has the mean of x and the variance of x. And then let's fit the normal on samples. Great. And you can see the mean is close to 1/2, which is the mean of the uniform distribution on 0, 1. Here we get an example where we call the function returning a tuple, but often you want to take the returned tuple and pull out the constituent parts so you can use them for some subsequent computation. So the thing you might naively do is to call that function and assign it to a tuple, and then say pull out the pieces. The mean is in index 0 and the variance is in index 1. And then maybe using an interpolated f string, you might print out the mean is m and variance b. Right? This is a little tedious. So again, Python has introduced a special syntax for easily destructuring tuples. And basically you do that by writing a tuple on the left-hand side of assignment where the elements are variables instead of values. So we're going to do something like m comma v equals fit normal samples. And then we'll do the same print statement. And we get the same result much more concisely. There's actually one more convenience with tuples, which is in many cases, it's not necessary to put the parentheses around a tuple, and Python can figure out that you actually mean a tuple. So, right, we saw 0.5 midpoint gave you a tuple, but now if we go back and we remove the parentheses, we see we still get the same tuple. And this also works in destructuring. So we'll just take that exact same example and we'll remove the parentheses. And then when we run it, everything is great. Tuple destructuring. Okay, so now we're going to go on to dictionaries. Dictionaries are another compound data structure that map keys to values. In Python, a dictionary is written with curly braces and colons between the key and the value. Let's look at a little example. So imagine we're doing an analysis and we have some samples that we're analyzing, and it's a case control analysis. So some of the samples are cases and some of the samples are controls. And so we're going to use a dictionary to map our sample ID to an indicator 0, 1, whether or not it's a case. So we're going to say sample is case, right? And this is going to be a dictionary. So we're going to use curly braces. And then we're going to say sample ID sample 0, sample ID sample 0 is a case. Sample 1 is a case. And let's say sample 2 is not a case. So we give it 0. And let's print out the dictionary. And we see we get the dictionary with 3 entries, sample 0, sample 1, and sample 2. Okay, so what are the operations you can do on a dictionary? So one of the things you want to do is given a sample ID or a key, you want to get the corresponding value. And that's just the square bracket index notation, right? Sample 1 is a case. If you ask for a sample that's not in the dictionary, again, Python is going to check for errors as it runs. So if we pull out some random thing, we get a key error, and the error is that this key is not in our dictionary. You can also assign dictionaries, much like you can assign lists. And again, you just use the index notation on the left-hand side. So you would say sample is case. Let's insert a new sample, sample 3, and that one is going to be a control. Great. Now let's look at sample is case, and we see, lo and behold, we have a fourth entry in the dictionary corresponding to sample ID sample 3. You can also delete elements from a dictionary. Say sample 1 withdrew from our study, so we need to delete it from the dictionary. And so you use the delete operator, del. And then let's print out sample is case afterwards. Just like you could iterate through lists, you can also iterate through the parts of a dictionary, but there are several parts. So the first thing to note is you can treat a dictionary just like a list, but when it's treated like a list, its elements are the keys of the dictionary. So we use for loops to iterate through lists. So let's just use a for loop to iterate through the keys of dictionary. For key in sample is case. So we're writing the same thing that we would write as if it were a list, but we're actually putting a dictionary in the thing that we're iterating through, and it's just going to iterate through the keys. So we're going to print out k, and we see we get sample 0, 1, and 3 because we deleted 0, 2, and 3 because we deleted sample 1. So sometimes you don't want to iterate through the keys, you want to iterate through the values. So there's a method on dictionaries called values that gives you a list of all the values. So if I do for v in sample is case dot values, now we get 1, 0, 0, which are the values. And finally, you might want to iterate through both the keys and the values. And Python calls those, I call those the entries. You can also call them the items. So we're going to say for key value in sample is case dot items, print k comma v. So note here that we're using the no parenthesis tuple destructuring syntax in the for loop to break apart the key and the value. So what items actually returns is a list of tuples, of pairs, tuples with 2 elements, which have the key and the value. Let's print that out, and we see we get basically the contents of the dictionary. There's one more thing that will show up in the Hail tutorial that you should probably know about. There's a special value called none, which is used by Python essentially to indicate that a function does not return a value or that a value is possibly missing. And so in the Hail library, you'll find that none is used to indicate that a value was missing for whatever reason. And when you evaluate none, it doesn't print anything out because there's nothing there. That should cover the basics of Python we'll need for the introduction to Hail. And hopefully that was a useful introduction if you plan to start using Python more seriously. I look forward to seeing you during the rest of the workshop.